So in the last video lecture, we looked at the brittle Coulomb-Mohr theory, which was itself a version of the ductile Coulomb-Mohr theory. So it's the Coulomb-Mohr theory is the larger class. Ductile and brittle are two versions of the same theory. And then the brittle Coulomb-Mohr theory is then modified into another theory, and this is called the modified Mohr theory. So this will be the last one we do, and it's slightly less conservative than the brittle Coulomb-Mohr theory. The modified Mohr theory actually expands the second and the fourth quadrant, and this is based on what they see happen out in the real world. So they see a lot of failures happening in right around right around this area and right around this region. So the BCMT, if you look at BCMT, this was in the second quadrant, this is it, and in the fourth quadrant, the boundary is right there. But they actually see a lot of failures happening outside of it. A sigma B would actually plot here. So they expand that, and that is the modified Mohr theory. So that is what this MMT is. So it's just another version of the BCMT with the second and fourth quadrant expanded. How do they expand it? How do they get? So that expansion is actually this. If you look at it here, so all of this is an extra area that is available according to MMT. On the fourth quadrant, it's this yellow area right there. So it replaces this line by two straight lines, this and that. And it does the same thing here, two straight lines here and right there. So what is that point? That is sigma negative S of ut divided by n. Right there. So that forms the basis of these two. So the safety envelope for the plane stress plane stress case is shown here. The BCMT and the MMT are both plotted, and you can see that the MMT has a larger area available in the safety zone than the BCMT does. So it's a less conservative version of the BCMT. The equations for this are in the books. They're not listed on the slides, but they are in the book. And where are they? They're actually in if you look at equation 532, A, B, and C. Those are case 1, case 2, and case 3. The cases are slightly different than when you look at the rest of the theories. The three cases are actually not the cases are the same, but they kind of deal with it slightly differently. So there will be an example that I want to do after this, but the modified Mohr theory equations in the book for the plane stress case are equations for the 532, A, B, and C. Okay. So let's do an example after this, and that's all I'll have. So this will be the last thing I do from this chapter. So. This is an example. This is a component. It's an impeller made of a brittle material. The S of ut is 30 kSi, 30 kpsi, and S of uc is 90 kpsi. The state of stress at a critical point in the impeller is sigma x equals negative 15 kpsi, sigma y is 10 kpsi, and tau xy is negative 15 kpsi. And the question is plot the BCMT and the MMT safety envelopes for a safety factor of 1.5, and then after that find out if the impeller is safe or unsafe at that point. So let's plot the safety zones for this brittle material of S of ut 30 kSi and S of uc 90 kSi for a safety factor of 1.5. So I want to plot it here, but let's find out what they need to be. So what I will do is, given material is S of ultimate tensile strength is 30 KSI. The compressive strength is 90 KSI. N equals 1.5. Therefore, the extents of the plot, when you do the plot, you'll look at S of ut divided by N, which therefore is 30 divided by 1.5 is equal to 20 KSI. And S of uc divided by N, which is 90 divided by 1.5. That is 60 KSI. Okay. So let's work with that. Going back to our plot, I'll try and use the entire area. Let's see how that works. Entire plot area. Every grid line will be, well, let's see, 1, 2, 3, 4, 5. 5 is 20. So every grid line is 4 kpsi. Let's try to see how this would work. The axis lines, that's your, let me try it one more time. Just make it straight. Let's see if we can get it straight. Sigma B, the first thing, and sigma A will be right there. No, that's not right. Let's try one more time. Let me erase everything, start over again. This is the one that's getting to me. Let's see. Okay, that's a good one. No, that's good. Leave it there. So that's sigma A, sigma B. This is sigma A axis, and this is your sigma B axis. And on that, let's do, so 20 right there, 20, negative 60 therefore is here at the very end, and negative 60 over at the bottom is right there. So let's join them with straight lines, and that would be your BCMT safety envelope. That's good. So these lines have to be straight, so that's good. That's another one. That's it. Straight line down. And this. And that's good. So this is your, maybe I should do it there. This is your BCMT safety envelope. This is 20, 20, minus 60, and negative 60 here. And let's also do the MMT safety envelope. Let me choose a different color. And what what that would be is a straight line from there to here. No, that's not good. Let's see if I can do it again. Yeah, that's good. And another one from there to there. Yep. And similarly from here to there. And another one from there to here. Okay. And the rest of it, the first and the third quadrants are the same. So you may want to just do it here. That's good. Another one over there. That's good. And that. So that one there is your MMT. Now let's look at the point. So the stresses at the point, sigma x, sigma y, and tau xy respectively are negative 15 kpsi, 10 kpsi, and negative 15 kpsi. So using that, let me see if I can write on the side here. So sigma x is, again, skip the units, negative 10. Sigma y is, let's see, no, sigma, that's not right. Sigma x is negative 15 kpsi. Sigma y is positive 10, and tau xy is negative 15 as well. Okay. Given this, your Mohr circle center will therefore be negative 2.5, 0. I'll have you verify that. And the first point on the circle A is sigma x, tau xy, which is negative 15, negative 15. So using that, create the Mohr circle. The radius of the Mohr circle, call it R, is equal to 2.5, even this, I think it should be 19.5. That would be the radius of the Mohr circle. Therefore, the two principal stresses from the Mohr circle, sigma A will therefore be, the larger one will be, on this side, 17 kpsi or ksi, and sigma B will be negative 22 kpsi or ksi. And that's what we'll use to plot on here. Okay. So let's see, we're negative 22 on sigma B and positive 17 on sigma A plots. So I said every grid line is 4. So 4, 4, 8, 12, 16, and 17. So 17 seems to be kind of right there on sigma A, and negative 22, 20, 24, 22 will be exactly at the center of this. So, and if you do it to scale, that's what will be very useful. And let me see if I can extend this. That point is therefore right there at the intersection of those two green lines. So you can mark it. Yep, right there. So what does that mean? That means it's unsafe according to BCMT, but it's safe for a safety factor of 1.5 according to MMT. It plots inside the cyan area, but it plots outside the red area. Okay? So, answer to this question is, going back to the question itself, is the impeller safe or unsafe at the critical point? So according to BCMT, the answer is it's not safe, it's unsafe, and according to MMT, it's safe. So the next part of the question is, so anyway, it didn't plot on any of the lines. So what is the safety factor then? that was used for whoever came up with this. So what will estimate the safety factor now using BCMT and MMT? So let's do that. So first let's use BCMT. The equation for that is sigma 1 divided by S ut minus sigma 3 divided by S uc, and that should be less than equal to 1 over n. So we had sigma a for this question. Sigma a was 17 ksi, sigma b was negative 22 ksi. For that reason, this therefore is sigma 1, this is sigma 3, and sigma 2 is 0. So your question now, this is 17 divided by 30 as of ut. According to this question, this is some kind of cast metal, minus negative 22 divided by 90 less than equal to 1 over n. So what does n have to be? N should be less than equal to let's do the math. And what do you think? Because the question was, it was unsafe. The question was, is it safe at 1.5? The answer was no. So it is. So the implication is that the safety factor is less than 1.5. And let's see if that's the case. So it's 17 divided by 30 minus 22 divided by 90, so it's plus 22 divided by 90. And inverse of that is n, and it is 1.23. So the safety factor that was used was 1.23 or less. It'll be safe for all of these, according to the BCMT. Okay, and then let's look at. Let's keep this on the side. So let me write this down here. N is less than 1.23. Okay. Let's look at MMT now. For this, I'll refer you to equation 532 in the book, and there are 3 parts to this. There are 3 parts to 532. So which one do we want to use? That depends on. It's not really case 1, case 2, case 3. It's not that clear cut. So first of all, we know that sigma a is equal to. Let me write that down. Sigma a is equal to 17 ksi. I'll skip the units here. Sigma b is equal to 22 ksi. Minus 22 ksi. So sigma a is more than 0, sigma b is less than 0. So obviously it's not equation 532c. It's either 532a that you have to use or 532b. The other thing they ask you to do is look at this ratio. The absolute ratio of sigma b over sigma a. So it's negative 22 divided by 17, and you don't have to solve this, just is it more than 1 or less than 1? So absolute is, you don't look at the signs, so it's 22 divided by 7 really, and that is 17, not 7, 17, and that is a ratio, it's 1.29, so it is more than 1. So if it's more than 1, then I'm looking at equation 532b, not a. A and b, they're both for sigma a more than 0, sigma b less than 0, but 532b is if this ratio is more than 1, then use that equation. So it's really in the fourth quadrant when that happens. And you see where that point plotted. It did plot in the fourth quadrant, and it was safe according to MMT. So the safety factor could be anything more than 1.5. It wasn't on it. It had been on the line, on the MMT line, then it would have been a safety factor of 1.5, but it was not on the line, it plotted way inside of it. So the safety factor obviously is more than 1.5, but that's the quadrant where it plots. So this equation 532b is the equation for the fourth quadrant of that plot. And what is that equation? Let me write that down. So that is S of uc minus S of ut divided by S of uc multiplied by S of ut multiplied by, this whole thing is multiplied by sigma A, and then you have sigma B divided by S of uc, and that should be less than, for it to be safe, less than n, 1 over n. Although the equation is the equation of the line in the book, so it's equal to 1 divided by n, but the safety condition is this. So this is your safety condition in the fourth quadrant according to MMT. So writing it out, this is S of uc is 90, so it's 90 minus 30 divided by 90 multiplied by 30 multiplied by 17 is S sigma A minus negative 22 divided by 90 is less than 1 over n, which would give you n is less than equal to, let's do the math here, negative 90 minus 30 divided by 60 divided by 90 divided by 30 multiplied by 17 plus 22 divided by 90, inverse of that is 1.6. 1.61, 607, so I'll say 1.61. Let me write this part again. So, according to brittle Coulomb-Mohr theory, the safety factor, I did write that down, it was n equals negative, n is less than equal to 1.23. So at 1.5, obviously, it'll tell you it's not safe. But the MMT safety factor, MMT says anything less than 1.61 is okay. So at 1.5, it told you, when we did plot it, it came out to be safe. So that's how you use these. That's how you use these safety plots. We've done a few of these. What I want to do is also talk about this in class. Maybe solve maybe 2 more problems on Friday when I'm back. And I would have expected you to have taken a look at these 3 files that I will be posting, and we'll talk about selection of static failure criteria. It's easy. Then again, there are 2 big classes. Some of these are meant for ductile, some of them are meant for brittle stuff. MSST, DET, and DCMT for ductile. MNST, the maximum normal stress theory, the brittle Coulomb-Mohr theory, and the modified Mohr theory. They're all for brittle, but then there are certain conditions where you want to use one and not another, and that is all dependent on how conservative you want your estimates to be. So ductile, if you look at it here, this is from the book. So if you look at this, ductile on this side, brittle on that side, and what's this? This is the strain at failure. So 5% is what we said. If it's more than 5%, then it does extend a whole lot. Then it's brittle failure. This is strain at failure, the 0.05, but it's in percent terms it'll be 5. So this is that strain at failure term. So brittle and ductile are classified accordingly. So if it's ductile, the next question you want to ask is whether S of YT and S of YC are the same. If they are the same, and that will be the case with steels, then you go this route. Down there, you want a conservative estimate. If the answer to that is yes, then you use maximum shear stress theory. If the answer to the previous question was no, then you would use DET, the distortion strain based theory. And if your answer to this question, S of YT is equal to S of YC, if the answer to that is no, then the only theory that you can use is the ductile Coulomb-Mohr, so DCMT. On the brittle side, there are only 2 choices. They don't really they don't even classify MNST. So your only options are really, unless, and this is what we'll do in class also, unless I do ask you to use MNST, don't. So it's either the modified Mohr theory, which is the less conservative version, or the brittle Coulomb-Mohr theory, which is the more conservative version of the Coulomb-Mohr class of theory. So the CMT, this is the Coulomb-Mohr theory, that's the parent theory kind of. So there's a ductile version, brittle version, and then a modification of BCMT. You can look at it that way. So yeah, so less conservative, in that case use BCMT. No, more conservative use BCMT, I'm sorry. More conservative use BCMT, less conservative use the modified Mohr theory. It just expands the space. That's it. So we'll talk about the selection of failure criteria when I get back on Friday, and we'll maybe solve a few questions. And I'll take questions from you. So I will expect you to have taken a look at these files I've posted, go through them, and then if you have any questions, ask me on Friday. Okay?